fine. So I'm going to start by welcoming you all. Good morning, good afternoon, good evening. Probably you're surprised that we are having such welcoming. And why I'm saying good morning, it's because, well, at my place it's just perfectly noon, but probably we are having people with different, we have participants from Australia, Middle East, Mexico, Brazil, Lativa. So we try to be as inclusive as possible. So on behalf of CPEX Global, I'm Anastasia, and I would like to welcome you all to ISO 12647, heading for printing process, conformance, and standardization. You might all know that in Germany, there are 250 printers that are ISO certified. So this is important to be ISO 12647 if you are associated with the printing business, either flexographic, offset, or rotogravure. So in this session, we have an amazing trainer, Dr. Abhay Sharma. Hello, welcome.
Good morning.
Who has an amazing professional experience in color management and that particular ISO implementation. In this session, he will provide you insightful learning for various parts of that, requirements, implementation criteria, etc.
I'm going to, in a moment, give you this quiz. I'll just go through these slides here, and here is a question coming up for you. So we're gonna have to do a task here in the class in a seminar today, and these three colors are in 3 dimensions, and I'm gonna ask you which one is 1, 2, and 3. So we need to wake up and now pay attention. This is a exam. Anastasia, you have any rewards for us if we get this right?
I can smile for you.
Okay, thank you. I was hoping for some coffee or a nice dessert.
I don't think I can send coffee via via internet. Yeah.
So we're joking, folks, but this is the fundamental system. So here's a chance in this seminar for you to understand this. You'll keep seeing it, keep hearing it, but not everybody knows how these numbers work. And there's some real good reasons to know how these work. And I'll show you at the end of this series of slides. So this is the LAB system. It's pronounced L star, A star, B star, or CLAB. So that's how we pronounce it. These are the only 2 ways that we really should write it. This is a 1-dimensional slice through that 3D color plane. And basically from plus A to minus A. And so having minus numbers, really my students can't deal with minus numbers. They don't know what a minus number is, but we're clever people on this seminar. So we have positive numbers to describe red colors. We have negative numbers to describe green. It can go from plus 100 to minus 100. And then this is a 2-dimensional graph, and we can have plus B values and minus B values. So hue changes around the circumference. We have different colors around. Saturation changes from the center outwards. L star goes from 0 to 100, but L star is not shown here. L star is shown here. So we're just looking at this 1-dimensional plane, kind of a slice through an orange here. And so if we have a value, and so yes, Photoshop actually shows minus 127 to plus 127. That's because it's an 8-bit, saving as an 8-bit integer. And so that's 256, 255 levels. Okay, so for this color here, we would have coordinates of L star we don't see, but we would have 50, and then perhaps also 50, 50. So plus 50, we would move along here, and then plus 50 again, we'd move up here. The way I explain it to my students is that we go into a house, we walk along the corridor and then up the stairs. So into the hallway, along the corridor, and then up the stairs, but basically it's X and then Y. If we had a green color, it would be minus 80 and then plus 40. So this color is specified by minus 80 plus 40. Is everybody okay so far? So if we had 8060, a red color, the L star is not shown. This is a two-dimensional diagram, so we ignore the 54. And so 80 is 80 along and then 60 up. And so we get 8060. For a green, we have minus 80. And then, so we get that color there. So let's just do this once more. When you get these LAB numbers, when you look at them, here's how you would use them. You would say that so 8060 would be plus 80 and plus 60. And that's where that color is. If it was a green, it could be minus 40. So digital values can have any of these numbers. Okay, so then this is our quiz. Anastasia is gonna tell us a joke. Smile if you get this right. So try to match the numbers to the colors. You have a two-dimensional representation and a three-dimensional representation here. Very easy. What is number one? Number one has L star of 50. So that's the vertical axis. So there's a color that's halfway up, and then it has 0A and 0B. So it moves very little away from the central axis. And
I
so,
can see a lot of correct answers.
Wow, yeah. Okay, so correct. Everybody that said one is gray. And so typically when you look at these LAB numbers and you see them in anywhere, quickly seen the first letter, the first number tells you how light it is. So 20 is dark, 70 is the lightest, 50 is mid-tone, exactly mid-tone, 50, neutral gray. And then if A and B are very large, then there's a color. If they're very small, then it's a neutral. So good. So 5000, quite a few correct answers that it's gray. And everybody should just kind of know that. So when you go to McDonald's and somebody says your order is $3, you know, that's about right. If somebody says your order is 300, you'll go, what? That's not right. So we need to know ballpark looking at LAB numbers. So good. Whenever you see like number one, a mid-tone, then 50 is a mid-tone, 90 is very light paper, 20, 15, 17, 20, L star is black. And A and B will be 0 if it's right down this central core, a neutral. Lots of people are saying 2 is green. So can anybody, are you brave enough to unmute? And those that said 2 is green, explain how you came to that conclusion. So anybody that said 2 is green?
2 is green. When you go to an A minus value, A minus is going towards green. A plus or A positive is going towards being red. So
good,
in my way of thinking, I always see A minus is greenish. A positive value is red, much like B. B minus is blue, and B plus or B positive is yellow.
Correct. Yeah. Okay. So take us through the 70, minus 60, 50, the values of the second color. So how did you?
The second
you
color.
You just guessed. Yeah.
No. The second color. Yep. So the L70. So that's showing it's quite sort of light. So it's high up towards the lighter end of the tone scale. But minus 60 is going out towards being greenish, and then 50 B is going towards being yellowish. So it has to be green.
Great. Correct. Yes. Did everybody understand David's explanation? So of course, if we say that 1 is 50, then 70 has to be higher than 50. So that's a clue as well. So there's only one color that's above that. But exactly as David said, instead of coming to the plus A, we've gone to the minus A, and then we've gone up to plus B. So it's 3 dimensions, so kind of funky, but correct. 2 is green. Sandis, would you like to explain 3? And so we have many clues here. We have the lightness, and then we have A and B coordinates. Or anybody else like to? Yeah, Sandis, are you going to explain green? 3?
I think it's not hard to explain because the first value 20 on axis L, it's quite low.
Good.
So the color should be dark. Then we are going to axis A, which is plus 60, something about red, and then B axis plus 50, which is, I don't know if it's if I can call it red or magenta or anyway, sure. This is very dark.
Yeah,
I'm sorry,
dark bloody color.
Great, good. Thank you for unmuting there for a few moments. Perfect. So folks, do we understand that? There are many clues that we can eyeball these colors with, and Sam is absolutely red. So 20, you can see. So immediately it has to be much darker. So there's a differentiation between color and lightness. So this 20 is just talking about that it's darker. The green was 70, so it's just much lighter, irrespective of the color. And the 50 L star is halfway up. And so we distinguish the lightness, first of all. Number 3, we talk about it being very dark, but it is very colored. So it can be dark, but it has a high color value. And we saw that as using this AB system. Here's A, it's plus A, and then 50. So on a 2-dimensional diagram, it was about here, but we don't see the L star, and that's there. Folks, I hope that we can use the LAB system either specifically or generally. And generally is just to look at the L star. If the A and B are large, then it's far away from the central axes, it's got a color. And so we use these two together, but basically there's a line, hypothetical, theoretical line. L star just tells us about where it is on this X, how high up or how low down. And then A and B tell us where it is, how far out, and how colored it is. So very useful. All standards are used this way, and that's what this is about. And here's how you can use it. So in this 3-dimensional space, when we have these two colors specified by their LAB, we look at the numerical difference from one to the other. And if it's 1.8, they're very near each other. If it's 4.6, they're far away. This is a bit exaggerated. But basically, if we have two colors, then the difference in LAB is a single number. It's very helpful for us. And all the standards are specified in terms of this number here. I'm just going to come back to this graph on the right here. But here's, as LAB is a perceptually relevant way to represent a color, when it is used to compute delta E, we have a single numerical value that corresponds to a visual perceptual color difference. And I would add here, and all standards talk about a delta E tolerance to meet an ISO standard. Generally speaking, 1 is just noticeable. We don't really achieve that much. 2 is for proofing, a close match. 2 to 6 is generally what we're printing at. 6 to 9 is getting to the top level. It depends on what the color is. And then beyond that would probably not be acceptable, but it depends on what industry you're in. In England, there's Marks and Spencer, and the color of the thread on the button and the thread and the color of the shirt has to be within 1 delta E. And so different industries, the car, where the paneling or the upholstery matches the external color, it all depends. But very broadly, here is what we may see. What can we use this for? Here's what we can use this for. Do you see that the delta E between these two colors, 1 and 2, is 2.9. Between 1 and 2 here is also 2.9. But what would we say about this? They've both got these particular colors. It's not the ones in the diagram here, but these both have a lot, the same color difference, these two colors, which one is going to be more difficult to control on press? So let's look at these. First of all, we're looking at this L star value, and then we're looking at the color. Where does the, yeah, anybody who chatted earlier or hasn't chatted, can you unmute and tell me what I'm trying to say here on the right? Two colors have the same delta E difference. One is going to be very easy to control on press, to correct, and one isn't, to bring them closer together. So if I don't have any volunteers, here the difference is only in the lightness. And so just by increasing the density, increasing the ink a bit, we can get from 48 to 45. So just by changing the ink film thickness, we can change and get these closer together. So they won't be at 2.9 if our tolerance is 2. But here, it's not the lightness, it's the color. There's a big difference in the color. And so to move something in color, maybe 1, 2, or 3 colors CMY that we're going to need to move. And which direction do we move? We're not sure. But here, if something is darker, you want to make it lighter, you change the density. If it's too high, it's too light, then we increase the density and it drops. So 45, this is opposite way. High number is 90, 100, 0 is down. So basically, this is just a ink film thickness change because it's lightness. But here, their lightness is okay. It's a color value that is different, and that means adjusting the CMY. So just looking at the delta E isn't always helpful on press to correct stuff. We may use looking at the individual LAB values. So this is the system that's used for all of our work. Okay, so here is some images on the left. Here is the LAB system. So I just drew those, I just showed you those dots, and they're in this system here, this LAB system. Let me quickly open a profile so you can see. So here's the LAB system. We just used it. Here are the axes that we used. It was positioned like this. Here's A, B, this is L star. As we get lighter, do you see it gets a white, lighter, darker at the bottom? So we can look at the gamut, and all of the standards talk about a gamut. In general, we have RGB gamuts. We have RGB gamuts that are bigger. So here are images. They typically are in RGB and they're bigger. The CMYK print gamut is smaller. And so we see that here. And so what we have in gravure printing and all printing is different paper types have different color gamuts. And do I have some, and so you have many profiles, and the profiles contain the gamuts. Let me find what I wanted here. I want to get two paper types. I got them yesterday, and I had coated 3 and coated 5. No, I can't. Oh, here they are. Coated 3 and coated 5. Right. And so let me make this a bit bigger. And so here's different levels of coated paper. And if we look at this, we can see, I'm going to stop this spinning. So here's the difference in the number of colors that we can add that we can get. So here are 2 paper types, paper 3 and paper 5. And so coated 3 and coated 5, coated 5 is the lower quality, a worse level. And here we can see the number of colors that we add to the color gamut by using this better quality paper. And so here is the amount of colors that, and this is the same inks, but different paper stock. And so here's the increase in color gamut. And basically there are 5 for gravure printing that we can choose from, and each one will have more colors. Well, so why do we care? Well, these images also have a color gamut. So if we look at the sand image, it will take a few moments. And then if we look at the balloons, and so we're going to look at the gamuts of these images. So the sand image is has some very high L star. There's a bit of reflection here on this shell, but basically it's not very colorful in terms of LAB. If we look at the balloon image is very colorful and has lots of colors. And so really you can't tell the customer that they can only choose one type of image, but we have to contend with that. And then if we look at the gamut of this coated 5, some of the colors in the balloon image are out of gamut. But if we only wanted to print the sand image, then that gamut is possibly going to be okay. Do you see many of the colors in the balloon, or sorry, the sand? Yeah. So the sand, we could actually get most of the colors in our CMYK print process. You see only a little bit of the sand is out of gamut. So it's a relationship between what people are printing and the achievable gamut on press, but especially it gets critical. For example, here, the woman image. So this is the woman image. And here she has a black dress. So that's down the bottom, highlight skin, highlight hair, red lips. And so here are the red lips that are coming right out here. Here's the gold from the dress. I don't know about her fashion sense with this gold, but here's the gold from the dress. Now this may be Maybelline Max Factor Clinique that is worried about the red of the lips. Maybe that's what the ad is for, this lipstick. So then in that case, is this, sorry, I don't know if this is, let me shrink this a bit. So here on the screen, you can see it because the screen gamut is big and the customer will see it, will approve it, will go, oh, that's fine. But if you look at the print gamut of gravure, you'll see that many of the colors are out of gamut. And that could be okay for the black dress, the blonde hair, but if this was the lipstick that we want and it's out of gamut of the print process, then that's going to be a problem. And gravure 5 gamuts that are specified are quite small. And so this is what the problem we would have. Here, the customer will see it in RGB on their screen. So they'll see the colors and they'll, yeah, that's fine. They'll go right up to the hair, the blonde hair, the red colors for the lipstick are fine. But after you've looked at it, then it goes to press and we see some of the colors are out. And so that's why the gamut and the paper, you can get a bit more with coated 3. And in fact, they're a bit bigger than that, but each paper type is going to make a difference. So we have to know that with the, and obviously we'd try to go to the best paper that we need. But if you're just doing this sand image, then any paper type really is going to be okay for that. So this is the importance of the paper and the inks. It makes the gamut volume, and that helps us deal with images of different types because they can be anything from the balloons image that looks like that is as colorful as this. Anastasia, did you understand what we are talking about here?
Why are you asking me? You should ask our guests.
That is true. That is true. Has anybody played with this software? Very powerful to help explain to customers and explain to your team what we'll do. David, I'll come back to that over the break. Let me look at where that was, filler content. What color spaces have these images used? Good. So every, so it sounds very good. Every image has an associated profile, and I can't remember what these were, but they were RGB images, so there'd be an RGB associated profile, usually sRGB, but a better one for a lot of us to use is Adobe RGB. Good. So every image must have an ICC color profile with it, and that's what is used to display the colors in LAB. Good question. Oh, Gulf Carton have this, David Crowther has this. Good. So you've used this. Here's a good way to use it. Great program. A bit expensive, maybe $500–600 for the different versions, but we'll do this and many other tricks. Okay, Anastasia, break time.
Exactly, you are right, break time. So 15 minutes for everyone. So I guess 35 past your time zone hour. See you later.